Hello. Hello. Hi, Shivani. Good evening.
Good evening, sir.
Actually, if you have some doubts, in on topics in previous classes, please feel free to ask.
So actually,
Hmm.
I'm not able to study linear algebra.
Ah,
My
okay.
exams were my exams were going on this week, so I did not study anything. So today I don't have any doubts.
Oh, nice, nice, good. No, anytime. If you have doubts, no, in the beginning of the class or towards the end of the class, you can always ask.
So maybe next week I'll ask.
Sure, sure. Yeah. So it is 6 already. Perhaps we'll start at 6:02. So today I'm planning to solve questions on eigenvalues. So until last class, we were. Oh, I'm in my lab and let me see. There was a Meet Auto Admit plugin. Let me download that. Please give me just 2 minutes. I'll just download this extension so that. Okay. Yeah, I think should we get started? So today I think from since the beginning, right? Today is the first class. Yeah. So today is the first class. We are going to discuss about eigenvalues. Let me close the other tabs. So I am in my lab today and I do not have a writing device. So what I'll be doing is I'll be writing in my iPad and I'm projecting the screen, the Jamboard here. So hopefully as I write, it will sync real time. Okay. So as I mentioned, today we'll be solving three questions on eigenvalues. So all of these questions are asked in gate only, right? Now the first question is very simple. They have given us an upper triangular matrix. I think now you must be familiar with what upper triangular matrix is. In the previous class, we saw a use case where you will be interested to convert a given square matrix to upper triangular matrix, and from there we saw how to obtain inverse of a matrix, right? And also we saw how to solve system of linear equations. I hope you remember row reduced echelon form, etc., etc. Now, it turns out that upper triangular matrices are kind of nice matrices and they have lots of properties, right? Now, in this question, they are asking us to find the eigenvalues of the given upper triangular matrix, right? Now, given this matrix, we can make use
Excuse
of,
me, sir.
yeah.
So are you sharing screen?
Oh, sorry, sorry. I'm not sharing it, sir. Yeah, is the screen visible now?
Yes, so now it's visible.
Thank you. Thank you for the alert. So, okay, let me repeat. So, in this question, we are given a 3 cross 3 square matrix, and for this matrix, they want us to find the eigenvalues. Right now, what I was saying is this is the upper triangular matrix, and in the previous class, we have seen what upper triangular matrix is in the context of solving system of linear equations. Right, and there we also saw that upper triangular matrices can be used to compute inverse of a square matrix also. Right now, this was a multiple choice question. Now, like for solving eigenvalues by taking the characteristic equation is not at all advisable in gate, especially for matrices of size 3 cross 3 or more. Reason is, in generally computation of eigenvalue is kind of compute intensive. So what you should do is refer some material, collect all the properties pertaining to eigenvalues, eigenvectors. You should remember those properties, and also you should know when and how to apply these properties to obtain results. Right now, it turns out that for upper triangular matrix, you can simply, for in particular for this matrix, you can simply read the eigenvalues from the leading diagonal of the matrix. Right now, moreover, we have actually for any matrix, not alone, I mean not only upper triangular, for any matrix we have um, sum of eigenvalues equals trace of the matrix. Right now, I'm writing some properties here. So given a square matrix A n cross n, right? Now sum of eigenvalues, right? Summation over I equal to 1 to n. Sum of eigenvalues will be equal to trace of A. What is trace? Trace is the sum of the elements along the leading diagonal of the matrix. Right now, second property you have is product of the eigenvalues will be equal to determinant of the matrix. Right now, we can use these two properties to kind of eliminate other options in the question, and thereby conclude that 1, 4 and 3 are the eigenvalues for A. Right, why? Because in the question, if you look at the options, we want the eigenvalues given in the option to adhere these two conditions, these two conditions. And okay, one may ask me, like, how did you compute determinant of matrix? Right, trace is very straightforward. Trace, you just sum the elements along the diagonal entries, so you'll get 1 plus 4 plus 3, that is 8. You know, trace is very easy. But how do you compute determinant of a upper triangular matrix? It turns out determinant of an upper triangular matrix is equal to product of the entries along the leading diagonal. Right, so in particular, determinant of A will be equal to 1 into 4 into 3. Now you can use this property to kind of like state the eigenvalues for an upper triangular matrix easily, without having to go to the write the characteristic equation explicitly and finding the roots of it. That is a tedious process, and it will take a lot of time. So this is why I'm saying this topic in general, they may not ask you to find eigenvalues of 4 cross 4 matrix. They, even everybody knows that that kind of question cannot be solved in, not even 5 minutes. Right, rather questions will always be of this type, that you apply some property and you get the result within seconds. Okay, now is there any question on this slide? Okay, if not, I will move on to the second question of the day. Now this is rather very simple. Now here what they have given us basically a 2 cross 2 matrix, and they have specified the eigenvalues of this matrix. Now they want us to fill in the entries corresponding to x and y. I hope the question is clear. We need to fill the entries x comma y. Is the question clear? Is there any doubt on the question?
No, sir.
Yeah. Now, can you tell me, like, we saw two properties earlier, right? Regarding trace and determinant of a matrix. Can you apply those properties to this matrix here? Yeah. Okay. Now first tell me what will happen when you apply the trace condition. Trace of A should be equal to sum of eigenvalues of A. Sum of eigenvalues of A. Right? What is trace of A?
2 plus y.
Exactly. So 2 plus y will be equal to sum of eigenvalues is 12. Now from this linear equation, we immediately find that y equals 10. Right? Now let's apply the second condition. What was second condition? Determinant of A equal to product of eigenvalues. So RHS is immediately clear. 8 into 4 is 32. What is determinant of A?
20 minus 3.
Exactly, right. 20 minus 3x, right? Now this will give us minus 3x equals 12, and from this we get easily x equals minus 4. Now just because you know the relevant properties of eigenvalues to be applied to this question, you can easily obtain answer in not even 1 minute, right? If you had known, let's say this question occurred in gate, and if you know that these two properties are relevant for eigenvalues, you would have solved this question in 30 seconds. All right, is there any doubt in this question? Okay. If there is no doubt, I had only planned three questions for today. So if there is no doubt, we'll move on to the last question, and perhaps we'll end the session with the last question. This third question is kind of complicated. Actually, not very complicated. We just have to prove if if the given matrix structure forms a group. I'll tell you what group means, etc., etc. Okay. In general, let me explain the question to you. So here, uh, we are given a upper triangular 3 cross 3 matrix, right? Where the entries below the leading diagonal are all 0, and we have a condition that ABC together will not be equal to 0. Now, this means that earlier, I told you one property. For an upper triangular matrix, determinant can be read by multiplying the elements along the diagonal of the matrix. Now, in the question, they are giving us an indirect hint that determinant of these matrices is not equal to 0. Right? It's a matrix structure clear to everybody. So basically, what we are considering is a set of 3 cross 3 matrices such that they are all upper triangular in nature, and further those upper triangular matrices are invertible, or those 3 cross 3 upper triangular matrices have determinant not equal to 0. Oh, okay. This plugin is not working. Yeah, okay. Let's just hope this plugin admits everybody. Yeah. Um, yes. So is a question clear to everybody? We'll come to the question. At least is a matrix structure clear to everybody?
Yes.
Yeah. Now the question is, what does the set of such matrices represent? Right? We need to answer if these set of matrices form a semi-group or a monoid or a group. Now, an immediate question is, when will you call a set as semi-group? When will you call a set as monoid? And when will you call it as a group? Right? So, uh, what you call depends on these four properties that I have listed here, right? What are they? First is closure property, second is associativity, third is identity, and fourth is inverse, right? You just have to understand, like by heart, which properties apply to which kind of group, right? Basically, if closure and associativity is satisfied, we call the set as a semi group. In addition to closure and associativity, if identity is also satisfied, we call such a group as monoid. In addition, if we have inverse, we call such a group as group. We call such a set as group. Now, the task in this question is to find out the set of upper triangular matrices such that they are invertible, form a group or not. That is the task, right? Now, I'll explain these properties: closure, associativity, identity, inverse. Along the way, as I prove, this set of upper triangular matrices is indeed a group, right? Now, every group we need to be specified an operation, right? And in this question, the operation that we are going to use is matrix multiplication, right? Let me go to the next slide. So, more formally, we consider a set. Sorry, we consider a set S equal to set of all matrices A in R n cross n, or or rather in this question R 3 cross 3, such that A is upper triangular and um, determinant of A is not equal to 0. Right? Now question is, does this set S comma matrix under does this set of all set of such matrices under matrix multiplication operation form a group or not? Right? Now let's start this by checking if this group admits closure property. Right? What does closure property state is, if you take any two matrices, let A1, A2 belong to S, we want also A1 into A2 to belong to S. What do you mean by this? We want, whenever you obtain a matrix by applying multiplication operation to two elements in the set, the resulting matrix should also be upper triangular, and further its determinant should also be not equal to 0. So for firstly, is closure property satisfied? I think you guys must be already knowing, because we have been dealing with upper triangular matrices. So basically, we know that product of two upper triangular matrices is in turn upper triangular only, and if both the matrices are invertible, basically A1 into A2 will also be invertible, right? You cannot intuitively you cannot produce a zero by multiplying two elements that are non-zero. However, you can produce a zero by multiplying two elements that are non-zero, by adding two elements that are non-zero. With multiplication, it is not really straightforward, right? That is why closure property is satisfied. Now let's see second property. Second property, what did we call? Identity, right? We say that a set under a operation satisfies the identity property if it is the case that there exists a special entry E in the set such that A into E equals A for all A in S, right? You need a special element called E such that if you use that element to apply the operation under consideration to any element in the set, then such an operation should return the element itself. right? And I think you must be immediately convinced that identity is indeed satisfied. Why? Why is identity satisfied? Because you have E equals 1 1 1 identity matrix, right? 0 0 0 0 0 0. Yeah, sorry about this structure. 0 0 1. Basically, convince yourself that this identity matrix is also a valid element of the set. Why? Because it is also upper triangular in nature and its determinant is equal to 1, which is non-zero, right? And we know that any matrix multiplied by identity is itself, and that is why identity property is satisfied. Now, the moment you satisfy this property, the considered set, that is S comma multiplication, will become a monoid. Now next, let's see if the set under the matrix multiplication operation is a semigroup or not. Now to check this, we need to probe the associativity property. Yeah, ink is taking some time to sync. Okay. We need to probe the associativity property. Now what is associativity property? Unlike previous properties where you needed two elements, in associativity we need three elements. Now what associativity says is, for any three matrices, for all A comma B comma C in S, we have A multiplied by B and then multiplied by C should be equal to A multiplied by B multiplied by C. Remember, associativity does not allow you to change the order of multiplication. You cannot multiply B cross A. This is not associativity. All associativity allows you to do is to change the order in which you apply the brackets. Right now, for associativity you don't really need the qualifiers of yeah, determinant not equal to 0 or anything. We in general know that matrix multiplication is associative, right? In general, matrix multiplication itself is associative. Sorry. And thus we can trivially extend this result to set of all upper triangular matrices, and that is why associativity property is satisfied, and moment you satisfy associativity property, this set forms a monoid, right? Now further, let's see if this set forms a group. Now for group we need inverse property, right? Now for identity you are searching for a element E. Similarly, in inverse property you will search for a element, let's call it I, such that for all A in S, we have I into A equals E, where E is the identity element that you chose earlier, right? Now, does inverse property satisfy for S comma multiplication? Any thoughts? Yes, right? Why? Because in the beginning, when we looked at the question, we had a condition that A into B into C will not be equal to 0. Now we know for a 3 cross 3 matrix that is upper triangular in nature and of this structure, the determinant of matrix follows from multiplying the entries along the leading diagonal. That is precisely ABC. Now because determinant of this matrix is not equal to 0, we have a guarantee that inverse of the matrix exists. Right? Now because of the given condition that ABC is not equal to 0, because ABC not equal to 0, determinant of A will not be equal to 0 for all A that belongs to S. Now this immediately implies that A inverse exists, or rather A inverse into A will be equal to I, identity matrix. That was the E element that it was earlier. Right? Now the moment you satisfy this property, we will call the set S comma into as a group. I hope the solution is clear to everybody. So let me recall what I have done. So basically we are given set of all upper triangular matrices of the form A B C D E F as shown here. Now further we are given a condition that product of the elements along the leading diagonal is not equal to 0. Right? Although they give the condition in a contrived format like this, ABC not equal to 0, you should remember the property that for a upper triangular matrix, determinant simply follows from product of the entries along the diagonal, leading diagonal. Right? Once you make use of the property, you should immediately realize that they are only considering a set of matrices that are invertible. Right? Now they have given us the set of matrices and they have given us one operation, that is matrix multiplication. Now the task is to find if the set together with the matrix multiplication operation forms a monoid or a semi group or a group. Right? Now for this we need four properties, that is closure, associativity, identity and inverse. What does closure mean? Closure means that whenever you take any two elements in the set and apply the operation on those two elements, the result should also belong to the set. Right? Now for this question we saw closure trivially holds. Second property is associativity. This also trivially holds because it holds for any matrices in general, and for associativity to hold, upper triangular is nothing special or anything. Right? Now third property we discussed is identity. Now for identity to be satisfied, you need to search for the element E. Now for matrices, the element E is straightforward. Basically, it is the identity matrix. Right? At last, we discussed about the inverse property. So for inverse, what we need is for all elements that belong to the set, there should exist a partner element which when multiplied will give us the identity back. Right? In general, this condition may not hold, but because they have given this qualifier like ABC is not equal to 0, this condition also holds. Thus, answer to this question is the set of matrices form a group. Is there any doubt?
No, sir.
Yeah. So these are the three questions I planned today. I think we completed ahead of time. If there is no further questions, perhaps we can call it a day.
Thank you, sir.
Yeah. Thank you. Thank you so much. Bye.
Thank you, sir. Yeah.